All right, so video 444, Brooklyn and Tynan who are gone. Rational functions. We're kind of switching gears, going from polynomials to rational functions. Be quiet. Polynomials to rational functions. Rational functions, here are some examples of them. A, B, C, right, like these three right here, okay? They get progressively more ugly, okay? But what it basically boils down to is if you graph this guy, do you remember what he looks like? If you graph 1 over x, what does he look like? They're little like boomerang-y things, right? Okay? They look like that. This is like, if you look at this poster, 1 over x, it's the L in my love poster, right? But really there's another one over here in the corner as well. Okay? Now, another thing to take into consideration with these little boomerang-y equations right here is that there is an imaginary dotted line this way and an imaginary dotted line this way. Those are called asymptotes. It sounds like a naughty word, but it's not. It has like an A-S-Y-M-P-T-O-T-E-S. So this one is a vertical asymptote. I call him a va, and this guy is a horizontal asymptote. I call him a ha, because one goes vertical, one goes horizontal. Va and ha. We'll talk about those later, but that's what the general graph of 1 over x looks like. Like the middle one here, this is just going to move him around and like stretch him out and like make him taller, skinnier, that type of thing, okay? But it's going to generally look like this. Now, one other weird thing is that if you have like f of x, instead of 1 over x, if you have 1 over x squared, he looks a little bit different. He looks a little bit different than this one. You know how he has changed? Any suggestions? No, not necessarily, but think about like if I'm plugging negative numbers in for x, and I square him, he's only going to be positive, right? So like basically this part down here is not going to exist, right? But he's going to be flipped up the other direction, so he will look like this. That's what 1 over x squared looks like, okay? So because we square him, he can't be negative, so this guy is just going to basically flip up there. Does that make sense? Okay? And he will be, still has a va and still has a ha, okay? But he will look like that, okay? Now the more numbers that you put in here, like this third one, may do some really weird, funky things, because sometimes you will have this happen, where you have like 2 vas, and we'll talk about each one of those, and maybe have a ha down here, I don't know. Sometimes you'll have like this happen, where you'll have kind of like a parabola thing in the middle, okay? So sometimes in really funky, weird cases, like when it has lots of numbers and it has all of this stuff, you might have a scenario when that happens, okay? It kind of looks like a smiley face upside down, right? No. Okay. Like a frowny face, whatever. Okay. So we'll talk about those later on, but basically it's going to involve some boomerangy things, maybe like a parabola in the middle if you have 2 vas, that type of thing, okay? All right, so going back to domain, we've talked about this before. We're doing domain, and there's 2 things that screw up domain. Okay, I'm going to drill this into your brain. 2 things that screw up domain, what are they? Negative and a square root. And dividing by 0. Negative inside a square root, division by 0. For this section only, we're worried about number 2, dividing by 0. There's no square roots in this section. This is all rational functions. We have only quotients, which are like have a numerator and a denominator. So we have stuff that we're dividing by, we're worried about dividing by 0. So in part A, I'm worried about this bottom part right here. That thing cannot be 0. So what can x not be? 0. If you cannot think about that and do that in your brain, you would just say, okay, x squared can't be 0, right? And how do I get x by itself? You take the square root, right? So x can't be, what's the square root of 0? 0. That's the algebra behind that, okay? Some of you guys can do this part in your head. This one, you probably can't do in your head, right? That one you probably can't, well, sometimes. So in this one, x squared minus x minus 6 can't be 0. That bottom part cannot be equal to 0. Okay? Now he is a quadratic function. What can I do to solve for x there? Add 6. No, I'm going to add the 6 over. Because he's quadratic. What? He's a simple trinomial. M and Liddell got it. What can I multiply? To get negative 6, but when I add them, give me negative 1. Negative 3 and positive 2. So I'm going to break them down like that. X minus 3, x plus 2. So I know that those values cannot be equal to 0. So x minus 3 cannot be equal to 0. And x plus 2 cannot be equal to 0. So x cannot be positive 3, and x cannot be negative 2. Does that make sense? Okay? So that not equal symbol is basically like an equal sign. It's just not equal, right? All the algebra stays the same. You can still add, subtract on both sides, whatever. That's what he looks like. Now notice in all of this, I am not concerned with the top numbers at all. The bottom number is all that I'm worried about. So as ugly as he is on the top, I don't really care, as long as the bottom comes out nicely, right? As long as the bottom comes out nicely. Good? Good? The top is irrelevant as of this point. Okay, I'm going to do one more example because they're going to throw this at you. So I'm going to put a little example up over here. Let's say I have 1 over x squared plus 4. Let's say I have that going on. What can x be and what can x not be? If I do that. Okay, so if you can't figure it out, x squared plus 4 cannot be equal to 0, right? So that means x squared cannot be equal to negative 4, right? And I could take the square root, but when does x squared give you negative 4? Never. So what can x be? Anything it wants to be, right? Right? It can't be the square root of 4i, right? Or basically plus or minus 2i. But when are you going to plug imaginary numbers in there? Never, never, never. So basically in this case they're trying to trick you because x can be all reals. X can be anything it wants to be, okay? Because we are adding 4, right? So even if I plug a negative number in for x, a negative number squared is going to be a positive number plus 4 is going to be another positive number. He's never going to be equal to 0. Now if it was minus 4, that would be a different story, right? If it was minus 4, it would be a different story. But since you're adding something to something that you're squaring, right, because you can't plug in imaginary numbers. Well, when are we going to do that? That's it, okay? So be careful of that. You're still kind of doing the algebra the same way, but some of you guys were able to figure that out right away, right? It can be anything it wants to be because you're never going to end up with 0. Okay, now I said that we have not dealt with the top until this point, right? Now is the point where we deal with the top, okay? So the bottom, I'll write a little key code in here. The bottom tells me the domain, like what can I and can I not plug in. The top is going to tell me the zeros. What's another name for 0? X-intercepts. Those are going to tell me where my x-intercepts are located, okay? So the bottom tells me my domain, the top tells me where my intercepts are located, okay? So, not only the x-intercepts, but the y-intercepts as well. We'll talk about both, okay? So let's do it with y-intercepts first because those are easier. And then we'll do it with x-intercepts, okay? So the y-intercepts, how do you find y-intercepts?
Wait, so we're just worried about the top right now?
Kind of. Well, I'll show you why we don't care about the bottom. I'll show you why. Okay? So when we're dealing with the y-intercepts, we plug x in, we plug 0 in for x. So 0 in for x. I'm going to do that for this problem. Y equals 0 squared minus 0 minus 2 all over 0 minus 1. Okay? Now, you might be able to do this in your head, and that is a-okay. Kind of like in a polynomial, really the last number is the only thing that you're caring about because everything else goes to 0, right? So this guy is 0, this guy is 0, negative 2 is on the top, but remember you also have a bottom. So you have negative 2 on the top and negative 1 on the bottom. Okay, everything else we don't care about. Everything else goes away. So negative 2 over negative 1, so what's the y-intercept? 2, he's going to touch it 2. Does he touch it 2 according to the graph? You betcha. That's consistent with the graph. They will not give you the graph, but I'm giving that to you so we can check our answers, right? Okay. All right, the x-intercept, you do the opposite thing, okay? And here's why the bottom we don't care about. If I'm finding the x-intercept, I plug 0 in for. So 0 equals x squared minus x minus 2 over x minus 1. Ugh. And I have to solve for x. So I'm going to, first and foremost, multiply the bottom to the other side, like Lynn said. Multiply by the bottom. And what happens to the bottom? The bottom goes away. Okay, that's why we don't care about the bottom for finding the intercepts, because no matter what, in all cases, the bottom is going to cancel out when you multiply to the other side, because then you can put 0 is just 0, right? Okay, so there's that, right? So really, the top is all that we're concerned about with doing the zeros, okay? If you want to skip that step, you sure can. Now we're looking at this, and we're trying to break them down. Right? To find our factors. Multiply to get -2, add to get -1. -2 positive 1. X equals x minus 2, and x plus 1. Okay, -2 times 1 gives me -2, -2 plus 1 gives me -1. What? Now, we're not doing domain, so we're not doing what x is not. We're doing where the x's touch, in this case. So, equals 0. So, x is going to be 2, and x is going to be -1. These are going to be my zeros, or where he touches. Does he touch the x at -2 positive, or -1 positive 2? -1 positive 2, right there. Okay? Does that make sense? So in all rational functions, basically you're setting 0 in, or you're plugging 0 in for y, but that's just going to make the bottom drop out every single time, because you multiply it over and it goes away. Right? Every single time. So the bottom is good for the domain, the top is good for the zeros, or the intercepts. Okay? All right, going down to the next one. All right. Example 3. And we're going to stop a little bit after this example. Okay? Without using a calculator, describe the graph of that function, this guy right here, when x equals 2. So, if we plug in x equals 2, we have 2 plus 1 over 2 times 2 minus 4. Okay? If we plug 2 in, we're trying to evaluate this thing at 2. So we're finding the y coordinate when x is 2. So we plug 2 in and we get 3 on the top and 0 on the bottom. What happens there? Yikes. Bad things happen. You can't divide by 0. He's undefined. And if we think about the domain, if I'm trying to do domain, right, I would say 2x minus 4 can't be 0, right? Okay, 2x minus 4 can't be 0, so that means 2x can't be 4 if I add the 4 to the other side, right? And x can't be 2, okay? Right? So we can't plug 2 in, but they're wanting us to figure out what's happening at 2. What is happening at 2? That's where the vertical asymptote is, okay? So, vertical asymptotes exist where domain fails. Okay, your vertical asymptotes exist where your domain fails. So basically what's going on with this thing is that we have this function. At 2? 1, 2, we have a va right here. And he's never touching that line. So the boomerangy things are going on the other side of that. Okay, now we need to decide, though, what's happening on either side of that thing, right? Like, is it going up on the right side, like really close to that line? Is it going down on the left side like the boomerangy thing should? Like, what's happening to him, actually? So, here's what let's do. Let's do this. Let's plug in. I'm going to do this real quick. Take out your graphing calculator. We're going to use the table feature, which is going to make this really nice and fast for us. Okay? Really nice and fast for us. I know, I still have lots of tabs, but I have less than yesterday. I did delete some because they're bigger.
Whoa.
Like the tabs are bigger. Okay? Okay, so we're going to use that table feature of our calculator. So go into your calculator. On. We're not going to graph yet. Go to y equals. Actually, we're not going to graph at all. On. I need it on. On. Turn on. Y equals. Okay, go to your y equals. We're going to type in this equation. Okay? We want to type in this one right here. This is what we're typing in. X plus 1 and then 2x minus 4. Okay? But when you do that, you need parentheses. X plus 1. You're right. Divided by 2x minus 4. Okay, so do parentheses around those. This is what mine looks like. X plus 1, 2x minus 4. Okay? And then I want to show what's going to happen to this guy around the number 2. So rather than graphing him, I am going to go to table set. Okay, do you remember going to table? If I go to table, which is second graph, it will tell me what all those numbers are when I plug them in. So if I plug 0 in there, I get negative 0.25. If I plug 1 in there, I get negative 1. If I plug 2 in there, I get an error, which is what we just validated. 3 in there, I get 2. 4 in there, I get 1.25, etc., right? But I want to zoom in a little bit closer to 2. I'm going to go second window, which is that table set option. You remember doing that a long time ago? Right? Yours said error.
Let's get your stuff while on.
That too is
That's what it says.
Supposed
It should
to.
say 2. Well, it's supposed to, right? That's what it's supposed to.
Figure it out
Over
now.
there.
So I want it to start at, let's do start at 2, and I want it to go by 0.01, let's say. I want it to start at 2, and I'm going to go by 0.01. Okay? Good? Good, good? Now, go to table again, and we're going to zoom in on what's happening on either side. I'm going to go up a little ways so I can see this. Okay? All right, just wait a second. Just wait a second. So the error is still at 2. It's going to be an error at 2 no matter what. But to determine what's happening on either side of that, okay, on the left side of 2, which is 1.99, he's a really big negative number, right? That means on my graph, on the left side of this 2, he's like all the way down here, right? So he's probably doing something like this, right? On the right side of 2, which would be like 2.01, 2.02, 2.03, he's at 150 and at 75 and at 50. So what does he look like there? He's really tall and he's coming down, right? Like that. Okay, that's what he looks like. Does that make sense to you? On either side of 2, he's like split. He's really big negative. He's all the way down there. He's really big positive. He's all the way up here. Right? Does that make sense? Okay? So using that table feature, you can see what the numbers are when you plug them in. Okay, there you go. Let's go to the back side. Go to the back side. All right, vertical asymptotes. We've already figured this out. I'm going to write it again. Vertical asymptotes exist where domain fails. So, how do you find a VA? How do you find a VA? Vertical asymptotes exist where the domain fails. I don't know why I spelled domain wrong. Domain fails. Domain fails. How do you find the VA then? How do we find the domain? No, not necessarily. How do you find where the domain fails? What equals 0? When the bottom equals 0. That's what your VA is going to be, is when the bottom equals 0. Right? So domain, I want the bottom not to equal 0. Your VA is going to exist where the bottom is 0. Right? Okay? So here are some examples of this. I have a VA here. I have a VA here. I have a VA here. So this is just showing you what can happen. This is the scenario that we were talking about before, like at the bottom of the first page. The one that we just got done doing, they're splitting and they're going opposite directions. But I can have the case where this is happening, where they're both going the same direction, or they're both going the same direction, right? They're both the same on either side of that line. That's why we need to check that to make sure that they're both like going opposite directions. One of them was negative, one of them was positive, of course. We know he's doing the middle scenario. Okay? So that's what can happen. All right. Now, let me give you this scenario right here. Let's look at this example and then we'll stop. This scenario right here. Okay? X squared minus 4 all over x minus 2. This is my example. Okay? This is my example. So if we're checking domain, we would say x minus 2 cannot be 0, right? X minus 2 cannot be 0, which means that x cannot be 2, right? Okay? If x cannot be 2, my VA, my vertical asymptote, is what? x equals 2, right? X equals 2 is the line where my va is. Except for this one. This is the only exception to the rule. X minus 2 is not a va. Or x equals 2 is not a va. And I will show you why. Okay? This is the only time your va is not what the bottom doesn't equal, right? In this case, it looks like our va should be x equals 2, but it's not, okay? Here is the only exception to the rule. If I look at this guy and I factor him down, well, I'll just do right here. You see this thing right here? X squared minus 4, they factored down into those two pieces. What is x squared minus 4? He's a difference of squares. I'm going to put that in here. Difference of squares, right? We factored him down. The difference of squares for x squared minus 4 is x plus 2, x minus 2. Now, it is not a va if he cancels out of both the top and the bottom, right? Okay, so notice that both the top and the bottom had an x minus 2 that could cross out. If it can cross out of both the top and the bottom, it is not a va. It is actually a whole. Okay, look here at this line. You see the little hole right there? That's my hole. So it is not a vertical asymptote. It is actually a hole in the graph. What? We're going to type that one. Okay. So that's the only time your va is not the bottom equal to 0 is if it crosses out of the top as well. And that's when a hole exists. Okay. In a real life scenario, a hole would exist. Given the scenario, let's just look at this graph, okay? If you're looking at this graph and you're saying, this is the amount of money that you pay to go to this amusement park, but on your birthday you pay nothing, right? That would be a hole in the graph because you're supposed to pay this amount of money, but on your birthday exactly you're going to pay $0. Does that make sense?
Is that actually a thing to do?
I don't know. Well, like it's like Applebee's. Going to Applebee's, you get a dessert. Your dessert costs this much, except if it's your birthday, then you get a free dessert, right? It's kind of the same type of thing. Maybe you're not going to get into an amusement park for free, but x equals 2 is a whole. So whole at x equals 2, and there is no va. That's just it. There's no va, okay? So that's the only trick to the thing. Is that it's not a va if it's a whole. So you have to also pay attention to that, okay? All right, we're going to stop there, and then we'll do the rest tomorrow. Good?
Great.
Beautiful, beautiful.